The concept of a fourth spatial dimension has long been a playground for mathematicians, philosophers, and science fiction writers. But the question of how a being existing in such a space might perceive reality has remained largely speculative. Recent advances in mathematical physics and computer science have begun to transform this speculation into a structured field of inquiry, integrating the principles of relativity with dimensional modeling to simulate how a higher-dimensional observer might experience time and space. This is the domain of four-dimensional perception and relativistic simulation, a field that challenges our fundamental assumptions about reality and pushes the boundaries of what we can model and understand. At its core, the study of four-dimensional perception is about understanding the perceptual constraints of dimensionality. Human perception is fundamentally shaped by our five senses, which provide the foundation for our understanding of reality within the constraints of three spatial dimensions. We navigate through length, width, and height, and time is typically perceived as a linear, one-way progression. However, beyond the boundaries of sensory perception lies the capacity for thought, an intellectual extension that enables us to conceptualize realities outside of immediate sensory access. Thought can be understood as a sixth sense, granting us the ability to hypothesize about dimensions beyond our direct experience. The central question becomes, how would a three-dimensional observer approach a thought experiment on perceiving a fourth dimension? And in what ways do the principles of relativity alter perception, particularly when time is treated as an additional spatial dimension rather than a separate construct? The mathematical framework for this exploration draws heavily on Riemannian geometry, which provides the essential tools for defining distances and intervals that characterize the curvature of spacetime in four dimensions. The metric tensor, a central concept in this framework, is essential for defining the geometry of 4D space. The differential element of spacetime in four dimensions is given by the equation ds superscript 2 equals g mu nu dx mu dx nu, where g mu nu represents the metric tensor and dx mu and dx nu correspond to differential displacements in the four-dimensional space. This equation is crucial for understanding the geometric properties of 4D space and forms the basis for subsequent modeling and simulation. Despite the impossibility of directly perceiving higher-dimensional spaces, this approach offers a structured method to represent how objects and spaces behave in 4D. Understanding four-dimensional space can be likened to the challenge of representing three-dimensional environments on two-dimensional screens, such as in video games. While the virtual world exists in 3D, viewers interact with it on a flat 2D surface. The 3D world is projected onto a 2D plane using visual cues like shading and perspective to suggest depth and spatial relationships. This analogy underscores the broader theme of our restricted perception. In the same way we perceive a 3D world through 2D representations, we can only experience 4D objects as partial, fragmented projections. For instance, a tesseract, the 4D analog of a cube, appears as a series of interconnected cubes when projected into 3D space. This is similar to how a 3D cube appears as a sequence of squares when viewed from various angles in a 2D world. Just as a 2D observer can only perceive slices of a 3D object, experiencing 4D space would likely require sequential or partial views of its components. These limitations in our perception hinder a full understanding of spatial relationships and movements within 4D space. Nonetheless, this analogy provides a conceptual framework for envisioning interactions with higher-dimensional spaces, much like players navigating a 3D world through 2D representations in a game. The implications of a fourth spatial dimension for perception are profound. A 4D observer would have the capability to perceive objects and events in ways that transcend our current understanding of spatial and temporal limits. One key distinction would be the ability to observe all aspects of an object simultaneously, enabled by the additional spatial dimension. This contrasts with our experience in three-dimensional space, where an observer must move around an object to perceive its full extent. In the 4D context, however, perception would be instantaneous and holistic, offering a unified view of a multifaceted structure. Furthermore, time itself could be perceived as an additional axis of spatial interaction. According to the principles of relativity, where space and time are unified in a four-dimensional space-time continuum. The introduction of a spatial dimension fundamentally alters temporal perception. A 4D observer could experience past, present, and future events as coexisting phenomena, similar to how we might perceive all slices of a 3D object simultaneously in a 2D plane. This reconfiguration has profound implications for the concepts of causality, motion, and existence, requiring a fundamental rethinking of how we understand the flow of time. The application of relativistic principles to the context of four-dimensional space introduces profound implications for the understanding of movement and perception. Just as the interaction between mass and the space-time continuum distorts our perception of time and space in the three-dimensional universe, these effects would be magnified in a 4D environment due to the complexity introduced by the additional spatial axis. In this higher-dimensional setting, the Lorentz transformation, fundamental to understanding the relativistic behavior of objects in 3D space, would extend into the fourth dimension. This extension would likely alter the observer's experience of both time dilation and spatial contraction in ways that are exponentially more intricate than in the 3D case. A 4D observer, encountering objects moving at relativistic velocities, would experience spatial distortions that are difficult to conceptualize from a 3D perspective. The curvature of spacetime caused by motion or the presence of mass could render objects as distorted or fragmented, with their appearance altering based on the observer's frame of reference. These relativistic effects, where spatial dimensions themselves could contract or warp under extreme velocities, necessitate the development of new frameworks for understanding kinematic motion in higher dimensional spaces. The Lorentz transformations describe how measurements of time and space change between two observers moving at a constant velocity relative to each other. For an observer moving at velocity v, the transformations are t equals gamma t, vx slash c superscript 2, x equals gamma x vt, y equals y, z equals z, where gamma equals 1 slash square root 1, v superscript 2 slash c superscript 2 is the Lorentz factor, and c is the speed of light in a vacuum. These transformations demonstrate how, as the relative velocity v approaches the speed of light, effects such as time dilation and length contraction become significant. For a hypothetical 4D observer, these transformations would allow them to perceive distortions in space and time analogous to how we, as 3D beings, perceive relativistic effects. For instance, as a 4D object moves through 4D space, an observer restricted to 3 spatial dimensions may perceive it as undergoing spatial distortions. Einstein's field equations from general relativity further describe how mass and energy influence the curvature of spacetime. In 4 dimensions, these equations allow us to model how gravitational fields might affect perception. A 4D being, influenced by gravity, might experience shifts in their perception of time and space beyond the human experience. Analogous to how a 3D object casts a 2D shadow, a 4D object, when projected into our 3D view, may appear distorted, much like a 3D object casting a distorted 2D shadow. The extension of general relativity to a 4D context provides intriguing possibilities for how beings in higher dimensions might interact with gravitational fields. Just as gravity influences the motion and perception of objects in our 3D world, gravitational fields in 4D might lead to additional distortions. For example, a 4D being might experience time dilation as a more complex transformation involving multiple spatial dimensions, where shifts in their perception could affect multiple axes in 3D space. To help visualize this concept, consider how a 3D object, when viewed from different perspectives, may appear distorted or foreshortened. In a similar fashion, a 4D object, when viewed through the lens of 3D perception, would produce distortions that are difficult to conceptualize in purely 3D terms. However, by applying the principles of relativity in this expanded dimensional framework, we can simulate and model how gravitational effects might operate in higher dimensions, broadening our understanding of the nature of perception and dimensionality. One of the most exciting developments in this field is the emergence of 4D sensor perception and relativistic image processing, a novel approach to position and depth estimation that extends conventional image processing in computer vision to include the theory of relativity. This approach combines temporal sensor and image data, processing diverse types of information in a novel model of 4D space through 10 different degrees of freedom consisting of 4 translations and 6 rotations. In this way, sensor and image data can be related and processed as a causal tensor field. This enables the temporal prediction of a user's own position and environmental changes, as well as the extraction of depth and sensor maps by related sensors and images. The dynamic influences and cross-sensor dependencies are incorporated into the metric calculation of spatial distances and positions, opening up new perspectives on numerous fields of application in mobility, measurement technology, robotics, and medicine. The complexity of sensor perception arises from various lighting, contrast, weather conditions, as well as dynamic and temporal aspects associated with the objects within the environment. Particularly the dynamics and associated time must be emphasized, as the perspective and positional relation between the objects change within the environment. Requirements such as maintaining safety distances, avoiding collisions due to moving objects, and calculating the shortest possible times at minimal energy consumption must be considered. If we want to consider all temporal aspects of information, a single coordinate system within Euclidean space is not sufficient. Rather, it is necessary to define temporal subspaces with a respective temporal axis. The Schlingel diagram, a novel tensor-specific diagram of 4D space, defines a novel approach of coordinate system in which space and time-dependent information are expressed by 10 different degrees of freedom, consisting of 4 translations and 6 rotations. This diagram considers the temporal aspects of space and extends the view of the Minkowski diagram and mathematical subspaces, in which higher dimensional information are represented as spatio-temporal coordinates. The Schlingel diagram offers the possibility of relating not only local but also temporal dependencies of information. Information can be described by 6 different planes of temporal and non-temporal dependencies. At rest, the measuring points are located between specific planes. If we relate the time between the systems, the measuring point shifts along the temporal axis. The temporal translation reflects temporal influences like time dilation or Lorentz contraction that occur when different inertial frames are related to each other. The resulting translation affects the geometry of space and their relative positions. The motion of tensor-specific comprises 4 translations and 6 rotations, in which the spatio-temporal measuring points are indicated on 6 planes, formed by 4 different axes. The resulting motion can be expressed as a 4-vector and contains 10 duets in 4D space. The resulting variable defines the 4-vector of the special theory of relativity, which depends on the magnitude of velocity. The framework presented in this research raises critical challenges in conceptualizing 4D perception, particularly in terms of interacting with multiple temporal dimensions alongside spatial ones. Such complexities introduce potential causal paradoxes, where past, present, and future could coexist, challenging traditional views of time, causality, and determinism. These theoretical challenges extend to practical implications in fields such as quantum mechanics, cosmology, and advanced simulation systems. The modeling of higher dimensional spaces holds promise for breakthroughs in quantum computing, where manipulation of higher dimensional states may unlock new computational capabilities. Additionally, exploring 4D space could yield significant advancements in gravitational physics, particularly in understanding phenomena like black holes and dark matter. Furthermore, simulations of 4D environments have the potential to revolutionize virtual reality and spatial computing by offering novel ways to visualize and interact with complex systems. The educational and practical applications of these concepts are already being explored. Virtual reality frameworks have been developed to study and learn relativity, allowing users to develop some intuition of the relativistic effects and the 4-dimensional reality of spacetime. These frameworks combine innovative rendering engines and non-Newtonian physics engines to compute relativistic effects in real time, enabling interactions between multiple relativistic objects, each moving with a different velocity vector, and allowing the user to interact with the objects and modify the scene dynamically. The originality of these 4D rendering engines lies in their capacity to efficiently store and retrieve non-simultaneous past space-time events that are visible by an observer at a specific location and at a given instant of their proper time. This technology makes it possible to actually experiment with the effects of relativity in a 3D immersive environment, helping students and researchers move beyond mathematical equations to develop a deep understanding of the theory's implications. The findings from this research indicate that a 4D observer would experience time and space in ways fundamentally different from 3D observers, with simultaneous access to multiple temporal dimensions. Mathematical models grounded in relativistic principles offer valuable insights into how distortions of space and time might manifest in higher dimensions. The integration of relativistic physics with mathematical modeling advances the understanding of how higher-dimensional beings might perceive their environment. Extending spacetime curvature to the fourth dimension provides new perspectives on dimensionality and interactions within 4D space, pushing the boundaries of traditional perception studies. Future research should focus on developing advanced simulations of 4D perception, particularly using virtual reality and quantum computing. These technologies present opportunities to test and expand the models introduced here, with potential applications in artificial intelligence, gravitational wave analysis, and complex system simulations. Further interdisciplinary research is necessary to refine these models and explore their practical implications. The study of four-dimensional perception and relativistic simulation represents a frontier where mathematics, physics, and computer science converge to explore the fundamental nature of reality. As we continue to develop more sophisticated models and simulations, we may find that our understanding of space, time, and consciousness is far more limited than we ever imagined, and that the key to unlocking the deepest mysteries of the universe lies in learning to perceive what we cannot currently see. The challenge and the opportunity of the coming decades will be to build the theoretical and technological frameworks that will allow us to not just calculate, but truly experience the fourth dimension, expanding human cognition and opening up new realms of scientific discovery and creative expression.